Hi everybody. This video will introduce us to another new statistical test called the one-way ANOVA. In this video, we'll first talk about what the one-way ANOVA test is, when we use it, and how it compares to the other tests that we've learned previously. We will then see how to calculate the one-way ANOVA by hand and how to interpret its results. This table on this slide gives us a quick recap of all 5 tests that we've learned so far this semester. The first test that we learned, the one-sample t-test, compares the mean of our sample against some expected number that we call mu. For example, if I wanted to know if the average amount of alcohol that students drink is different from 4.5 drinks per week, I could survey a sample of students, calculate the mean of that sample, and use a one-sample t-test to compare that mean against 4.5. A one-way chi-square test does something very similar, except we're working with a categorical variable instead of a continuous variable. For example, if I knew or if I predicted that 27% of students don't drink at all, I could survey a group of students, calculate the percentage of students in that sample that doesn't drink, and use a one-way chi-square test to see if that percentage is or is not different from 27%. Both of these tests only use one variable. The one-sample t-test uses one continuous variable, and the one-way chi-square test uses one categorical variable. The other 3 tests on this slide each look for a relationship between 2 variables. First, the two-way chi-square test looks for a relationship between 2 categorical variables, and what it allows us to do is compare percentages between 2 groups of people. For example, if I surveyed a large group of men and women and I asked them, do you drink alcohol, yes or no? I could calculate the percentage of women that don't drink and the percentage of men that don't drink, and I could use the two-way chi-square test to see if those 2 percentages are different from each other. An independent t-test does effectively the same thing, but instead of comparing percentages between groups, we're comparing means between groups. So if I surveyed a large group of students, some of whom live off campus and some of whom live on campus, and I asked them, how many drinks do you have per week? I could calculate the average number of drinks per week for students who live off campus and the average number of drinks per week for students who live on campus, and use an independent t-test to see whether those 2 means are different from each other. Most recently, we talked about the dependent t-test, where we're measuring one group of people on 2 different occasions to see if their mean changed between time 1 and time 2. For example, if I wanted to know if seniors tend to drink more alcohol than juniors, I could survey a large group of juniors, ask them how many drinks they have per week, and then 1 year later, when those same students are now seniors, recontact them, survey them again, and ask them that same question. I could then calculate the mean of how much they drank when they were juniors and compare it to the mean of how much those same people drank when they were seniors to see if their drinking behavior changed over time. Here again are the previous 2 tests that we've learned. The independent t-test allows us to compare the means of 2 different groups of people, and the dependent t-test allows us to compare the same group of people across 2 points in time. However, these tests are limited because they only allow us to compare 2 means against each other. What if we wanted to compare 3 or more means against each other? Or what if we wanted to measure the same group of people 3 or more times? We haven't yet learned a test that's capable of doing that. That's what the test we're going to talk about today allows us to do. So whereas the independent t-test only allows us to compare the means of 2 groups of people against each other, the between groups ANOVA, which is the test we're going to focus on today, allows us to compare the means of 3 or more groups of people against each other. So for example, if we wanted to compare how much men and women drink, we could use an independent t-test because there's only 2 groups. But if we wanted to compare how much freshmen, sophomores, juniors, and seniors drink, we would have 4 groups of people that we would want to compare, so we would have to use our new test, the between groups ANOVA. As a side note, there is also a test called the repeated measures ANOVA. This is the test we would use if we wanted to measure the same group of people 3 or more separate times to see how, if at all, their scores changed over time. We're not going to learn how to do that test in this class, but I wanted you to at least know that that test exists. Whereas a dependent t-test, we measure the same group of people twice. A repeated measures ANOVA allows us to measure the same group of people 3 or more times. Next week, we will learn yet another type of ANOVA test. Both of these tests, the between groups ANOVA and the repeated measures ANOVA, are referred to as one-way ANOVAs because in each case, they only have one independent variable and one dependent variable. Again, for example, if I wanted to see if there is a relationship between class year and drinking behavior, I would have 4 groups of people, freshmen, sophomores, juniors, and seniors. My independent variable, therefore, would be class year. My dependent variable would be how much people drink. Let's now talk about how to do the between groups ANOVA and some situations in which we would use that test. In one study, for example, the researchers wanted to know if people who own dogs differ in terms of their sleep quality. In this study, they included 3 groups of people. One group of people whose dogs sleep in bed with them, a second group of people whose dogs sleep in the same room but not in their bed, and a third group of people whose dogs sleep in a different room than their own bedroom. Over the course of 5 months, the participants in this study wore a device called an accelerometer that tracks the quality of their sleep. And what the researchers ultimately did is they collected data from that device and compared the sleep quality between those 3 groups of people. People whose dogs sleep on their bed, people whose dogs sleep on their floor but in the same room, and people whose dogs sleep in a different room. What they ultimately found is that compared to the other 2 groups, people whose dogs sleep in bed with them tended to have lower sleep quality. Here's another example. We know that there are 5 different flavors, 5 different kinds of taste buds that we have: bitter, salty, sour, sweet, and savory. In this study, the researchers wanted to know if having a particular taste in your mouth would make you more or less likely to take risks. So what they did is they randomly assigned each participant to one of 5 groups. They received either a bitter, salty, sour, sweet, or savory food to eat. Then, while that taste was still in their mouth, they played a game that required them to take a risk. In this game, they blow up a balloon on a computer screen by holding down the space bar. Holding down the space bar inflates the balloon, and the bigger they were able to inflate the balloon, the more money they would win. However, if they inflated the balloon too much, it would pop and they would win nothing. So their measure of risk-taking behavior was how much each participant was willing to inflate the balloon. What they found was that people who had previously eaten something that was sour were more likely to take risks, meaning they blew up the balloon more compared to the other 4 groups. Again, the reason we would use a between groups ANOVA in this situation is because the researchers were comparing 5 separate groups of people against each other to see how those 5 groups of people differed in terms of their risk-taking. The ANOVA test requires us to do 2 steps. Today, we're only going to talk about the first of those 2 steps, and on Thursday, when we meet again, we will talk about the second of those 2 steps. Here's an overview of how this test works. Remember that we use this test when we have 3 or more separate groups of people. We calculate the mean for each of those groups, and we want to know if those groups are or are not different from each other. For this test, our null hypothesis is always going to say that none of the groups are different, or in other words, all of the groups are equal to each other. So in the previous example, with 5 groups of the 5 taste buds, our null hypothesis would be that all 5 of those groups were equal in terms of their risk-taking. No 2 of those groups were different from each other. In step 1 of this test, we are looking to see whether we find something called a main effect. If we do not find a main effect, it means that none of the groups are different. They are all equal to each other. And in that case, we will retain the null hypothesis, and our conclusion will be that all of the groups are equal. If we do find a main effect, however, we will reject the null hypothesis, and our conclusion will be that the groups are not all equal to each other. In other words, at least two of the groups are different. However, if we find a main effect, that does not immediately tell us which of the groups are different from each other. All it tells us is that at least two of the groups are different, but it doesn't tell us which ones. In order to then determine which groups are different from each other, we have to carry out a second step called post hoc testing, which is something that we'll talk more about on Thursday. If we did not find a main effect, we already know that none of the groups are different, so we do not need to perform post hoc testing. Again, today we will only focus on the first step in this procedure, how to determine whether there is or is not a main effect. As we've done in previous weeks, I will now walk us through step by step how to calculate this test by hand. Specifically, how to determine by hand whether or not there is or is not a main effect. The good news for you all is that this is the last test that we will learn how to do by hand this semester. We will learn 2 more tests next week and the week after, but those tests we will only learn how to do in SPSS. We will not learn how to do those tests by hand. So today is the last day that we'll actually be doing math in here. The less good news is that of all of the tests that we've learned so far, this one requires the most steps. They're still not difficult, but there's a lot of addition, subtraction, division, and multiplication involved in calculating the results of this test. The first step, as always, is going to be to state our null hypothesis. In this example, we will try to answer the question of whether high school students, college students, and graduate students drink the same amount of coffee. Again, the reason we'd have to use a one-way ANOVA test here is because we have 3 groups of people: high school, college, and graduate students. Imagine we surveyed 15 students, 5 from high school, 5 from college, and 5 from grad school, and we asked each student to tell us how many cups of coffee they drink per week. Here's what the data look like. We have our 5 high school students in orange, our 5 undergrad students in green, and our 5 grad school students in blue. Beneath that, we have the answers that each student gave when asked how many cups of coffee they drink per week. Our null hypothesis is that none of these groups are different from each other, or in this case, that high school students, undergrad students, and grad students all drink the same amount of coffee. None of the groups are different in terms of how much coffee they drink. Our second step will be to calculate what's called the F statistic. Now, we've previously learned 2 chi-square tests, both of which used the chi-square statistic, and we've learned 3 t-tests, all of which used the t-statistic. The test that we're learning this week, as well as the test that we'll learn next week, uses a similar statistic called F. Here's what the F statistic tells us. First, you've heard me use the word ANOVA many times, but I haven't yet told you what exactly it means. ANOVA is an acronym for Analysis of Variance. The reason that it's called that is that the F statistic tells us about the ratio of what's called the between group variance and the within group variance. Now, that sounds real complicated, but it's actually quite simple. The between group variance tells us how different our groups are from each other. So how different are the means of our different groups? Within group variance tells us how much variation is there within each group. So if we look at each group individually, are the scores pretty similar to each other, or are the scores really spread out? So what I'll show you next are 2 extreme examples of when we might have a very large F statistic versus a very small F statistic. Imagine that we have three groups, and those groups look like this. We've got group 1 in red, group 2 in green, and group 3 in purple, each showing the distribution of scores within those groups. In this case, the means are quite different from each other. The means are quite far apart. So we would say there is a large amount of variance between groups. The groups are very different. Within each group, the distribution is very tall and skinny, which tells us that within each group, the scores are mostly pretty close together. As a result of that, notice how little overlap there is between the three groups here. Pretty much everyone in group 2 scored higher than pretty much everyone in group 1. And pretty much everyone in group 3 scored higher than pretty much everyone in group 2. So it's easy to look at this graph and say those groups are different. For that reason, we would end up with a very large F statistic in a situation like this. Compare that scenario against this one. We still have three groups, group 1 in red, group 2 in green, and group 3 in purple. But now the means are much closer together. So the amount of variance between groups has decreased. Within each group, we also have a lot more variability. In other words, each group is now a shorter, wider distribution. As a result, there's a lot of overlap between groups. Some of the people in group 3 scored higher than the people in group 2. Some of the people in group 2 scored higher than the people in group 3, and so on. So it's not easy to look at this graph and immediately tell that the groups are different. Maybe they're not. So in a situation like this, we would end up with a very small F statistic, and we would be likely to retain the null hypothesis and conclude that we did not find evidence of a difference. How exactly do we go about calculating the F statistic? As I warned you a few minutes ago, it's going to take a lot of steps. Thankfully, those steps are all pretty easy, and if we can keep our work organized, it'll make things even easier. Before I show you the formula for calculating F, we first want to make sure that we know all of the following things. First, we want to know the value of a number called K. K is just the number of groups that we have in our study. We also want to know how many people are in our study. Each group will have its own little n. So in this case, we have three groups. So little n1 will tell us how many people are in group 1. Little n2 will tell us how many people are in group 2, and so on. Big N is the total number of people in our study, or in other words, the number of people in all of the groups combined. We also have what's called a big T, or total score, for each group, which is just the sum of the scores within each of the groups. So big T1, for example, would be the sum of all of the scores of the people in group 1. Big T2 will do the same for group 2, and big T3 will do the same for group 3. We also have a number called G, which is the sum of all of the scores of all of the participants combined. Lastly, we have a number called sum of x squared. This is going to be the biggest out of all of these numbers. To calculate this number, we'll take each individual person's score, we'll square those individual scores, and then we'll add all of those squared numbers together. Now, if this isn't making much sense so far, don't fret. On the next slide, we're going to see how to calculate all of these numbers in the context of our coffee example. So here again is the data from our coffee study with our three groups, high school, undergrad, and grad school, 15 total participants. And for each participant, we know how many cups of coffee they drink per week. The value of K in this study, which tells us the number of groups, will be 3, since we have 3 groups, high school, undergrad, and grad students. There are 3 people in high school. I'm sorry, 5 people, my fault, 5 people in high school. There are 5 undergrads, and there are 5 grad students in this study. So the little n for each of those groups will be equal to 5, which tells us that we have 5 people in each of those 3 groups. In total, we have 15 students in our study. To calculate the total, or big T score for high school, we will add together the scores of our 5 high school students. In other words, if we think about these 5 high school students combined, how much total coffee do they drink per week? So we'll add together 2 plus 3 plus 0 plus 1 plus 4, and the 5 high school students in our study combined drink 10 cups of coffee per week. We'll then do the same thing for undergrads. Our 5 undergrads combined drink a total of 14 cups of coffee per week, and our 5 grad students combined drink a total of 26 cups of coffee per week. Again, all we're doing here is we're taking the scores within each group and adding them together. To calculate the value of G, which is our grand total, we could either add up all 15 of the individual scores, or we could add up the 3 T's that we just calculated, and in either case, we should get the same result. So if we add up 10 plus 14 plus 26, adding the 3 T's together gives us our grand total G, which is 50. In other words, the 15 participants in our study combined drink 50 cups of coffee per week. Lastly, we'll calculate the sum of x squared. The way we'll do that is by taking each individual person's score, squaring it, and then adding all of those squared numbers together. So for example, we would add 2 squared, which is 4, plus 3 squared, which is 9, plus 0 squared, which is 0, plus 1 squared, which is 1, and so on, 15 times. And this will give us our largest number yet. If we were to square all 15 of these numbers and add those 15 numbers together, we would get our sum of x squared, which is 228. Once we have all of the numbers that we calculated on the previous slide, we can calculate the F statistic using the equations that are shown in the source table. Before I show you the source table, I want to warn you, there's going to be a lot of formulas in here, but they're all pretty simple. And if we previously have calculated the numbers on the previous slide, calculating the numbers in this table will be very easy. All we have to do is plug in the numbers that we already know and gradually chip away at this table until we end up with our F statistic. Here's what the table looks like. In the first column of this table, we have 3 formulas, each of which calculates something called the sum of squares. From top to bottom, we have the between groups sum of squares, the within groups sum of squares, and the total sum of squares. In the second column, we have 3 degrees of freedom values. The top one is the between groups degrees of freedom, the middle one is the within groups degrees of freedom, and the bottom one is the total degrees of freedom. In the third column, we have 2 mean squares values, a between groups mean squares, and a within groups mean squares. And then finally, all the way on the right in the fourth column, we have what we're actually looking for, which is our F statistic. Now again, although this table may look very intimidating, as we'll see in a second, as soon as we fill in 2 of these boxes, the rest of these boxes fill themselves in very, very easily. All we'll need to do is know where to start and know which numbers to plug in from the numbers that we calculated previously. Let's start in the bottom left-hand corner of the table by calculating the total sum of squares, which is the formula that's highlighted in yellow right now. As you can see, in order to calculate the total sum of squares, we need to know 3 things. We need to know the value of sum of x squared, we need to know the value of g, and we need to know the value of big N. All 3 of these things are numbers that we already calculated a few slides ago. Here again is the formula for the total sum of squares. So all we need to do is take those 3 numbers and plug them into the formula. Our sum of x squared is 228, the value of g is 50, and the value of big N is 15. We then square 50, divide it by 15, and subtract that number from 228 to give us our total sum of squares, which in this case is 61.33. So we'll take that number, 61.33, and plug it into the source table in the appropriate place. The next formula that we'll tackle is the one at the top left, which is the between groups sum of squares. To calculate this number, we need to know the total score, or big T, for each group. We need to know the little n for each group, and we also need to know G, the grand total, and big N, the total number of participants. We also see the Greek letter sigma, which tells us that we will need to add together a number of things. Specifically, what we'll do is for each of those three groups, we're going to calculate the value of t squared divided by little n. Here's our formula again. For each of the groups, we know the total score as well as the little n, the number of people in that group. So our formula is going to look like this. For the high school group, the total score was 10, and there were 5 people. For the undergrad group, the total score was 14, and there were also 5 people. And for the grad school group, their total score was 26, and there were also 5 people in that group. We will add those numbers together, as shown on the screen, and then subtract g squared divided by n in the same way that we did before. When we calculate all of that out, we should get a between group sum of squares value of 27.73. We will now put that number, 27.73, source table as well, to replace the formula that we just used. Once we've filled in those two boxes in our table, the rest of the table is very easy to fill in. Let's next calculate the within group sum of squares, which is the box highlighted on the left. That number is just the difference between the two numbers that we just calculated. In other words, to fill in this box, all we have to do is take our total sum of squares, 61.33, and subtract the between group sum of squares, 27.73. Here's that formula again. We're just going to take the two numbers that we just calculated and find the difference between those two numbers. So when we subtract that out, we find that our within group sum of squares is 33.6. We can in our source table as well. So if we add from top to bottom, 27.73 plus 33.6 equals 61.33. We're now ready to fill in the second column of our table, which is the degrees of freedom. We know from a few slides ago that K tells us the number of groups that we have in our study. In this case, we had 3 groups in our study. We also know that big N tells us the total number of people in our study, which in this case was 15. So our between group sum of squares, which is K minus 1, is going to be equal to 3 minus 1, which is 2. Our within group sum of squares is going to be equal to big N minus K, which is 15 minus 3, or 12. And finally, our total sum of squares will be equal to big N minus 1, which is 15 minus 1, or 14. So from top to bottom, our degrees of freedoms will be 2, 12, and 14. Let's put those numbers in our table. Again, we can always double check by making sure that the first two numbers add up to the third number. 2 plus 12 is in fact 14. Next, we will calculate the two mean squares values that are highlighted in the third column. To calculate these values, what we'll do is we will divide across the table from left to right. So to calculate the mean squares between, we will divide 27.73 over 2. To calculate the mean squares within, we will do 33.6 divided by 12. So in each case, we're taking the red number on the left and dividing it by the black degrees of freedom to get the mean squares on the right. 27.73 gives us 13.87, and 33.6 divided by 12 gives us 2.8. Those will be our mean squares values, which are now shown in blue. Finally, we're ready to calculate our F statistic. The F statistic just requires us to take those two mean squares values that we just calculated and divide the top one by the bottom one. So to calculate F, we will take 13.87 and divide it by 2.8, and that will give us our F statistic, which is 4.95. So again, this table looks very intimidating at first, but once we filled in those first two values at the top left and the bottom left, the rest of the table was actually quite easy to fill in because all of the numbers in the table relate to each other in some way. We now have our F statistic of 4.95. The rest of the steps in performing this test will be very similar to the steps that we've done previously. We know that our F statistic is 4.95, but we need something to compare it against. So we'll be to calculate the degrees of freedom and to find our critical value to compare our F statistic against. For the chi-square test, we had a chi-square table to find the critical values. Same for the t-test. For this test, we have yet another table called the F table. This is the table that we will use to find the critical values when we're working with an F statistic. The first thing to notice about this table is that it's a little different than the tables that we've used previously. First off, all of the values in this table represent an alpha of 0.05, so that actually saves us a step. We don't have to worry about finding the value of alpha in our table. One key difference, though, is that for the F test, there's not one, but two degrees of freedom values. First, we have our degrees of freedom between, which is also sometimes referred to as the degrees of freedom numerator. Those are just two different names for the same thing. Whether we call it the numerator or the between groups degrees of freedom, the way we calculate that number is k minus 1. We also have our within groups degrees of freedom, which is also called the denominator degrees of freedom. The way we calculate that number is by taking big N and subtracting k from it. The good news here is we've already calculated both in the source table a few slides ago. We know that our between groups or numerator degrees of freedom is equal to k minus 1, which was 2. And we know that our within groups or denominator degrees of freedom is equal to big N minus k, which was 12. So if we find the corresponding rows in our table and we find where they intersect, that gives us our critical value for this test, which in this case is 3.89. The next step, as we've done many times before, is to compare our critical value against the F statistic that we just calculated, which will allow us to make a decision about whether to reject or retain the null hypothesis. So let's draw our F curve. Now, like the chi-square statistic, F can never be negative. It's always going to be either 0 or a positive number. So the curve for our F statistic looks very similar to the curve for our chi-square statistic. And we're only going to have one critical value, which will be a positive number. On the previous slide, we used the table to find that the critical value for this example is 3.89. So we'll put that on our graph. Back in the source table, we calculated our F statistic for this study is 4.95. If we plot that on the number line, we clearly fall within the green area, which tells us we are going to reject the null hypothesis, and our conclusion is that there is a main effect. In other words, what we've just discovered is that we compared three groups of students, high school students, college students, and graduate students, in terms of how much coffee they drink. We calculated the F statistic, we found a critical value, and we concluded that there is in fact a main effect, which tells us that those three groups of students do not all drink the same amount of coffee. In other words, some students drink more than others. Our last step will be to write up our results in APA format. Here's what that might look like here. Remember to always start by naming the tests that you did. A between groups ANOVA revealed that our three groups of students, high school, college, and graduate students, do not all drink the same amount of coffee. In other words, we did find a main effect here. The end of our sentence looks very similar to how it's always looked. We have our statistic, we have our degrees of freedom, and we have our p-value, which is either greater or less than 0.05. One key difference here, however, is that for the F statistic, we have 2 degrees of freedom rather than just 1. So in those parentheses, we're going to put 2 numbers separated by a comma. The first number, which in this case is 2, is the between groups degrees of freedom, and the second number, which in this case is 12, is the within groups degrees of freedom. After the equal sign, we have the value of the F statistic that we calculated, 4.95. And because we rejected the null hypothesis, we're going to say that P is less than 0.05 in this case. Notice that we did not include means for each of these groups. When we do a problem like this by hand, we're not going to include the means. However, on Thursday, when we do these problems in SPSS, we will include the means. We'll come back to that later. So after all that work, what we've determined is that our three groups of students, high school, college, and graduate students, do not all drink the same amount of coffee. However, what we don't know yet is which groups of students are different from each other. The fact that there is a main effect tells us that these three groups of students do not all drink the same amount of coffee. However, until we perform post hoc tests, we do not know which students drink more coffee and which students drink less coffee compared to each other. As I mentioned at the beginning of the video, we'll talk more about post hoc tests on Thursday, and we'll see how to perform those tests in SPSS. Before we do that, here's a quick overview of how exactly post hoc tests work. In this example, we compared three groups of people. And the fact that we found a main effect tells us that at least two of those groups, maybe all three of them, are different from each other. What post hoc tests will do is they will take our three groups and compare each of them against each other 2 at a time. So in other words, we'll look at every possible combination of groups to determine which ones are different and which ones aren't different. And there's a number of possible outcomes here. Maybe we compare all three groups of students and our post hoc tests tell us that all three groups are different from each other. High schoolers and undergrads are different, high schoolers and grad students are different, and undergrads and grad students are also different. A second possibility is that one of these groups is different from both of the other two. For example, maybe grad students drink more coffee than high schoolers and more coffee than undergrads, but high schoolers and undergrads drink the same amount of coffee as each other. A third possibility is that only two of these groups are different, but neither of them is different from our third group. So maybe, for example, high schoolers and undergrads drink different amounts of coffee, but neither of those groups is different from grad students. The point here is we don't know which of these is true until we perform post hoc tests in SPSS, which is something that we'll do on Thursday. You may be wondering, if we have three groups of people and we want to compare each of those groups against each other 2 at a time, why can't we just do 3 independent t-tests? We've already learned a test that can compare 2 groups against each other. Why can't we just do that test 3 times? Think way back to when we first talked about p-values. And we also talked about the different types of errors that we can make when we're deciding to reject or retain the null hypothesis. What we ultimately decided is that we can never be 100% sure that we made the correct decision when we decided to reject or retain the null hypothesis. In other words, every time we run a test, there is a chance, however small, that we're going to commit a type 1 error by incorrectly rejecting the null hypothesis when in fact there was no difference. If we were to perform 3 t-tests, that means there would be 3 times the risk that we would commit an error. That's the reason why statisticians use post hoc tests. Most post hoc tests are designed in a way that keeps the risk of error low while still allowing us to perform multiple comparisons. Let's now try another example. And this one I'd like you to try practicing on your own to make sure that you're comfortable calculating and interpreting the F statistic. As you know, my personal interest is in using psychology to improve the operation of the legal system, to ensure that justice is always served. When children are suspected to have been abused, as you probably know, or at least have seen on television, interviewers sometimes use dolls, like the ones that are shown on the screen, to help interview children about allegations of abuse. For example, the interviewer might hand the child a doll and say, "Show me what the person did," or "Show me exactly where the person touched you." And the child is expected to point to the doll, which helps them report the abuse that may have occurred. The belief is that these dolls are helpful, that they might allow children to describe body parts that they maybe don't have the vocabulary to describe, or maybe that they help children feel less embarrassed about reporting what had happened to them. Unfortunately, however, there is some research to suggest that these dolls may not work as well as they're thought to work and could actually be problematic in certain situations. This video, which you can watch by going to the URL shown on the screen, tinyurl.com/dolls212, reviews some of the research showing how the use of these dolls during child abuse interviews can actually be problematic. Pause this video now and take a moment to watch this YouTube video and see some of the studies and the researchers talking about those studies about why these dolls are potentially problematic. The video will start you at 3 minutes and 11 seconds. Please watch the video until at least 5 minutes. Okay, so as you saw in the video, these dolls, although they're believed to be helpful, can actually result in children reporting things that didn't actually happen to them, which can of course be problematic because it leads to false allegations of sexual abuse. So one problem with these dolls is that they encourage children to play, right? Kids are very imaginative, and when you give children a doll like this, it encourages them to engage in imaginative play and possibly talk about things or simulate things that didn't actually happen. That's a particular issue with these specific dolls, which are made with body parts that other dolls don't have. There is, however, a more fundamental problem here. In order for the dolls to work as intended, think about what actually is being required of the child. In order to use one of these dolls effectively to report where exactly they were touched, the child has to not only understand that the doll is a doll, they also have to understand that the doll is a symbolic representation of their own body, that the doll's arm is a representation of their arm, and the doll's chin is a representation of their chin, and so on. As you might imagine, that's a pretty sophisticated cognitive task to ask a young child to perform, because kids tend to be very concrete, whereas here we're asking them to do something that's very abstract and very theoretical. The second example that we're going to look at today addressed that very question. Do children understand that these dolls are not just dolls, but they're also meant to be symbols of their own bodies? Here's what the researchers in this study did. They recruited a sample of children, and they read each kid a story. And while they were reading them the story, at various points in the story, they took stickers and they put them on different parts of the kid's body. So here's a sticker on your forehead. Here's a sticker on your arm, for example. Later that day, the researcher gave the kids an anatomical doll, like the ones we were just talking about, and they asked each kid to put stickers on the doll in the same places that the researcher had put the stickers on them. So again, this is a way of seeing whether the child understands that their head is the doll's head, and that the doll's hand is a symbolic representation of their hand, and so on and so on. Our null hypothesis here is that our three groups of kids, there was a group of 2-year-olds, a group of 3-year-olds, and a group of 4-year-olds, those three groups of kids will all place the same number of stickers correctly on the doll. Here's our data. We have three groups, again, 2-year-olds, 3-year-olds, and 4-year-olds. Each group had 4 kids in that group, so 12 kids total in this study. And the numbers show us how many of the 4 stickers each child was able to correctly place on the doll. Pause the video and, using the data at the top of the screen, see if you can fill in the values at the bottom. What's the value of K, small n, big N, T for each group, the grand total, and the sum of x squared? Once you get those values, we'll go over them together. There were 3 groups in this study, so the value of K was 3. Each of the 3 groups had 4 children in that group, so each of the little n's is equal to 4. There were 12 total children in this study, so the value of big N is equal to 12. For the 2-year-old group, the 4 children combined placed 6 stickers correctly, 2 plus 1 plus 1 plus 2. For the 3-year-olds, the combined number of correct stickers was 11, and for the 4 4-year-olds, the combined number of correct stickers was 13. If we look at all 12 kids combined, they correctly placed 30 stickers between the 12 of them. Lastly, our biggest number, sum of x squared, we take each individual score, square it, and add them together. So 2 squared plus 1 squared plus 1 squared plus 2 squared plus 3 squared, and so on for all 12 kids. We get a value of 86. Now that we have all of these numbers, use the formulas from a few slides ago to start filling in the source table. Remember to start with the total sum of squares at the bottom left and the between group sum of squares at the top left. Our total sum of squares for this sample was 11, and our between group sum of squares was 6.5. We'd calculate those numbers using the formulas from a few slides ago. Remember that the within group sum of squares is just the difference between those numbers. So 11 minus 6.5 leaves us with a within group sum of squares of 4.5. Our degrees of freedom from top to bottom are going to be 2, which is k minus 1, 9, which is big N minus k, and 11, which is big N minus 1. To find our mean squares between, we'll divide from left to right, 6.5 divided by 2, and that gets us 3.25. To get our mean squares within, we'll divide 4.5 divided by 9, that gives us 0.5. Lastly, to get our F statistic, we'll divide 3.25 by 0.5, which leaves us with an F statistic of 6.5. Remember that we're going to need those top 2 degrees of freedom values to put in the table to find our critical value, so let's keep those in mind. Here is the table. On the previous slide, we found that the between groups, or numerator degrees of freedom, was equal to 2, and the within group, or denominator degrees of freedom, was equal to 9. So our critical value here is going to be 4.26. Remember that f can't be negative, like chi-square, so our curve looks like this. We'll put our critical value 4.26 on the curve and see how our F statistic compares. Our F statistic here was 6.5, so we will again reject the null hypothesis. What this tells us is that these three groups of children were not all equal to each other in terms of how many stickers they were able to correctly place on the doll. In other words, we did find a main effect here. What we don't know yet is exactly which groups of children were different from each other. All we know is that some kids were better at placing the stickers than other groups were. Here's how we would write up our results. We ran a between groups ANOVA, and we found that there was in fact an overall relationship between age and how many stickers the children placed correctly. Another way to phrase this would be to say that 2-year-old, 3-year-old, and 4-year-old children were not equal to each other in terms of how many stickers they placed in the correct places on the doll. Our F statistic is equal to 6.5, and remember we have 2 degrees of freedom values to include in the parentheses, the between groups, which is 2, and the within group, which is 9. And because we rejected the null hypothesis, we say that P was less than 0.05. Take a minute to check your own answer against this. Here are the actual results of this study. First, you'll see the researchers explain exactly what they did to the children who participated. They mentioned that they performed an ANOVA on the number of stickers that were placed correctly, and like we talked about before, the ANOVA is a 2-step process. First, the researchers established that there was a significant main effect of age. In other words, the 3 groups of kids that they studied, 2-year-olds, 3-year-olds, and 4-year-olds, were not all equal to each other in terms of how well they placed the stickers. Once they found this main effect, they performed post hoc analyses to see exactly which groups were different from which other groups. What they ultimately found was that the 4-year-olds did better than the 3-year-olds, and the 3-year-olds also did better than the 2-year-olds. In other words, as kids got older, they tended to be better at understanding that the doll was a symbolic representation of their own body, as evidenced by the fact that they placed more stickers in the correct places. Here's a graph that shows the means for each group. The 4-year-olds did quite well, the 3-year-olds significantly less well, and the 2-year-olds significantly less well than that. On Thursday, we will see how to perform this test in SPSS, including both how to determine whether there's a main effect, as well as how to perform post hoc tests to determine which groups are different and which groups are not.